Welcome to this explainer. You know, whenever we look up at the daytime sky, we see this brilliant, blinding fixture that has literally been there for every single day of human history, but we rarely stop to think about what it truly is. Today, we're not just looking at a source of light. We are exploring the incredible biography of our solar system's dynamic and entirely finite protagonist. The Sun is a massive sphere of hot plasma heated to incandescence by nuclear fusion. And its story is one of unimaginable scale, violent mechanics, and ultimate cosmic fate.
Okay, let's dive into this, because to really understand the Sun, we have to start with a number that is just absolutely staggering. When you picture the solar system, you probably picture the massive gas giants like Jupiter and Saturn, the vast asteroid belts, and all the rocky planets, including our own Earth. But the truth is, all of that put together is basically a rounding error. The Sun accounts for 99.86% of the total mass in our entire solar system. Everything else, every planet, moon, and comet, is just leftover debris from its formation.
And to sustain that kind of cosmic dominance, it requires an incomprehensible fuel supply. Every single second of every single day, this massive star converts 4 billion kilograms of matter entirely into pure energy. And it's not burning it like a lump of coal. It is literally wiping 4 billion kilograms of matter out of physical existence and transforming it into the radiation and light that makes life on Earth possible.
So, here is our roadmap for today's explainer. First, meet the solar system's boss. Second, inside the solar engine. Third, magnetic mood swings. Fourth, the Sun's ultimate fate. And finally, humanity and the Sun.
All right, Chapter 1. Meet the solar system's boss. Let's really grasp the scale of our star.
Let's be honest, the human brain isn't really built to understand cosmic scales, so grounding these mind-bending numbers against our home planet definitely helps. The Sun's radius is 109 times that of Earth. If the Sun were a hollow sphere, you could fit over 1 million Earths inside it. Its mass is about 330,000 times greater than Earth's, and because of all that mass, its gravitational pull is immensely powerful. To escape Earth's gravity, a rocket needs to travel at 11.2 kilometers per second. To escape the Sun's surface, you would need to reach an astonishing 617.7 kilometers per second. It is an overwhelming anchor in the dark.
Moving to Chapter 2, Inside the Solar Engine. Let's pop the hood on this hypercar and see how it actually generates power.
So the crucial point is the absolute center of the star. In the core of the Sun, the temperature reaches a blistering 15.7 million Kelvin, and the pressure is about 150 times the density of liquid water. Under these extreme conditions, a process called the proton-proton chain reaction takes place. Basically, hydrogen nuclei are smashed together to form helium. Every second, an unbelievable 600 billion kilograms of hydrogen are fused together. This is the fundamental nuclear fusion engine that keeps the entire star from collapsing under its own crushing gravity.
Now, what's really interesting about this slide is its sheer efficiency. When we think of a nuclear reaction, we usually think of massive, explosive power. But theoretically, the maximum power density at the center of the Sun's core is only about 276.5 watts per cubic meter. Believe it or not, that is roughly the same power density as a literal garden compost pile. A piece of the Sun's core the exact size of an average human would only generate about as much heat as that human does. The only reason the Sun shines with an almost incomprehensible total output of 384.6 yottawatts is simply because of its immense, unfathomable volume.
And getting that energy out, well, that's quite an ordeal. Let's map out a single photon's journey. Once created in the core, a photon enters the thick radiative zone. The gas here is so incredibly dense that the photon just bounces around, constantly being absorbed and re-emitted. This random scattering means it can take a single photon up to 1 million excruciatingly slow years just to cross this one layer. From there, it hits the convection zone, where hot plasma boils and carries the heat to the surface in thermal cells, kind of like a pot of boiling water. Finally, it reaches the photosphere, the visible surface of the Sun, and escapes into space as the sunlight that will hit Earth exactly 8 minutes later.
Chapter 3. Magnetic mood swings. Let's move outward to the atmosphere and explore some highly volatile space weather.
Methodically breaking down these outer layers reveals something pretty counterintuitive. If you map out the temperatures, the visible surface, the photosphere, is a very hot 5,772 Kelvin.
If you move further away from the surface into the next layer, the chromosphere, the temperature unexpectedly jumps up to around 20,000 Kelvin. But then, as you move even further out into the corona, the outer atmosphere, the temperature violently spikes to between 1 and 2 million Kelvin. This bizarre temperature jump leads us straight to one of the great unsolved mysteries in astronomy, the coronal heating problem. Imagine walking away from a campfire, and somehow the air a full mile away is thousands of times hotter than the fire itself. It completely defies basic logic. Currently, scientists theorize this insane heat is generated by the sun's complex magnetic fields. The two leading theories suggest it's either caused by magnetic waves traveling upward and dissipating their energy as heat, or by a continuous barrage of mini explosions called nanoflares releasing magnetic energy.
These twisting, turning magnetic fields actually drive the sun's 11-year cycle of activity. You see, the magnetic bands get tangled up because the sun rotates faster at its equator than at its poles. Eventually, they burst through the surface to create dark sunspots and massive solar flares. And this directly impacts us here on Earth. For instance, in the 17th century, the solar cycle mysteriously stalled, resulting in very few sunspots for decades, a period called the Maunder Minimum. This directly coincided with Europe's Little Ice Age, proving how intimately our climate is tied to solar moods. Today, violent coronal mass ejections from the sun can overwhelm our planet's magnetic field, potentially causing devastating disruptions to our electrical grids and satellite communications.
Chapter 4. The Sun's Ultimate Fate. It's time to examine the finite, inevitable lifespan of our star.
Let's move to and see how this builds across the timeline of our star's life. Born 4.6 billion years ago from a collapsing molecular cloud, the Sun is currently middle-aged. It's halfway through its stable main sequence phase. But in about 5 billion years, it's going to run out of hydrogen fuel in its core. Without the outward pressure of fusion, the core will shrink and heat up, pushing the outer layers away. The Sun will swell into a massive red giant. And the terrifying reality here is that about 7.59 billion years from now, its expansion will reach so far out that it will boil our oceans away, completely engulfing and destroying the Earth.
Following that massive expansion, the dying star will experience something called the helium flash. In a matter of just minutes, a violent ignition will convert 6% of the core into carbon. The sun will become highly unstable, pulsating, and eventually shedding its outer layers entirely, creating this beautiful, glowing cloud of gas known as a planetary nebula. All that will be left at the center is a naked, incredibly dense core called a white dwarf. This stellar corpse will slowly fade, radiating its residual heat for trillions of years until it eventually becomes a cold, silent black dwarf. Finally, Chapter 5. Humanity and the Sun. Let's bring this immense cosmic scale back down to our historical bond. And this brilliantly illustrates how our perspective on the sun has evolved over time. For most of human history, we looked up in pure reverence. The ancient Sumerians worshipped the sun as the god Utu. The Egyptians revered it as the falcon-headed Ra. We built grand monuments like Stonehenge specifically to track its movements and solstices. Slowly, though, our perspective shifted. In the 16th century, Copernicus correctly proposed that we orbit the sun, putting it at the true center of our cosmic neighborhood. Fast forward to today, and we're sending marvels of engineering like the SOHO satellite and the Parker Solar Probe to actually fly right through its scorching corona to gather real-time data.
It's really fascinating to look back at the very first attempts to strip away the mythology and understand the sun scientifically. The Greek philosopher Anaxagoras was one of the first to propose it wasn't a god riding on a chariot, but a physical object in space. He reasoned it was a giant flaming ball of metal, even larger than the Peloponnesian Peninsula. Now, of course, compared to the precise, data-driven plasma physics we've explored today, he was off by quite a bit. But it represents the dawn of human curiosity, the first spark of asking what this engine of life actually is.
Which leaves us with a profound realization. Everything we are, everything we have ever built, is powered by an engine that is steadily burning through its finite fuel. The sun provides our light, our weather, our food, and our time itself. As our magnificent star inevitably burns out into a silent black dwarf trillions of years from now, what will be the ultimate legacy of our fleeting moment in its light? Thank you so much for exploring this remarkable star with me. Keep asking questions, keep looking up, and I will see you in the next explainer.